Hello? Hello?
Hello?
Okay. Hi, I'm Nasib. Happy to introduce the TKS. Um, it's a it's been interesting watching them present. Every time I learn something new, so I thought it's a good opportunity to bring them in front of you guys. And I'll leave it there. Yeah.
So, hi everyone, my name is Shagun. I'm 15 years old, and today I'm going to be talking to you about computer vision, the intuition behind computer vision, and the integration of computer vision in multiple industries and fields. So, a bit about computer vision. So, computer vision basically gives the ability for a camera, computer, or system to have artificial human vision in order to analyze, detect, and classify images and objects. So there's actually two sections of computer vision, and the first section is classification, and this is image classification. So in hindsight, in this image, a convolutional neural network uses image classification to classify this picture as a cat. And the other section of computer vision is object detection. And essentially what object detection does, it identifies and classifies the objects in an image while localizing and finding out the location of the object in the image. So first I'm going to talk about image classification. And I actually got interested in image classification when I saw this picture over here. So essentially the intuition behind this picture is that if you look at the left side of the picture, you see a man looking directly at you. But when you look at the right side of the picture, you see a man looking to the side. And the theory behind this is that when your brain is trying to identify and classify images, it actually extracts key factors from the images in order to classify it. And that's actually how a convolutional neural network works in order for image classification. So there's 4 steps for a CNN, or a convolutional neural network, to do image classification. And the first one is convolution. So essentially, every image has a digital representation. And for the sake of simplicity, the input image is divided up into zeros and ones. And what happens in convolution is that you're actually trying to minimize the image in order to process it in your neural network. And what happens is a feature detector is inputted on a section of the image, and what the feature detector does, like the man who was looking straight and to the side, it tries to identify key factors in the image and find its similarities. So for example, in this image, the feature detector didn't find any similarities between the first stride of the input image. That's why on the feature map, it's a 0 is outputted. But if you look at this image, the feature detector found one similarity in the next stride, which is why on the feature map, a 1 is outputted. So essentially, the feature detector goes along the entire image and fills up the feature map. And essentially, there's more feature maps because there's multiple feature detectors that are put on the image in order to classify it. And all the feature maps together are noted as the convolution layer. Now the second part is max pooling. So when you want to train an image classification, for example, to identify and classify dogs and images, you have to train them on multiple images of dogs. But of course, all the images of the dogs are not going to be the same, and there's going to be some variations. For example, in one image, a dog's face is to the right, and in another image, the dog's face is to the left. So what max pooling essentially does, it takes into account all these variations, and it takes into account all the distortions, and makes the CNN flexible. And it does this through max pooling, which essentially takes a small box and it inputs it on the feature map. And when it inputs on the feature map, it takes the highest value matrices, and in this case, the highest value matrix is a 1, and it outputs it on the pooled feature map. And essentially, it goes through the whole feature map and outputs the highest value matrix on the pooled feature map. And in essence, it does this because it's trying to find the matrices with the highest similarities that we found between the convolution layer and the input image. And also by doing this, it reduces 75% of the information that is not needed during the CNN. So this is the completed pooled feature map, and there's also a number of different pooled feature maps, as there is a number of different feature maps, and this concludes into the pooling layer. So now the next step is flattening. So essentially, we want to get ready to input the features of the images and encode it into our neural network in order for it to be trained. So to do this, we have to get all of our pooled feature maps and flatten all the matrices to put it into the input layer of the artificial neural network, which is essentially the vector of features. So this is the basic structure and architecture of the neural network. And I was really interested in this, so I decided to create my own convolutional neural network to use image classification to detect images of dogs and cats. So I trained my neural network, but when you train your neural network, then what you want to do is that you want to input an image that the network has not been trained on before. So I inputted this image of a dog that the network has not been trained on before. In essence, what I wanted is that I want my desired output to equal a 1, because a 1 represents a dog and a 0 represents a cat. And sure enough, the neural network outputted a 1, which means that my neural network was optimized and it was accurate. So the second part of the section of computer vision is object detection. And as I mentioned before, object detection is understanding and classifying the objects in the image while also finding the location of the objects in the image. So before I go on to explain object detection, we first have to understand object localization. So object localization is localizing the object in an image, but only a singular object in the image. And it does this by outputting a bounding box on the object in the image. So suppose we're trying to use object localization to train a self-driving car. So in our training set, we'll have images of pedestrians, cars, motorcycles, and a background. But this cannot be it which is in our input layer and in our training set, because we're also trying to localize the objects in the images. So in order to localize the objects in the images, we need to add the bounding boxes. So when we add the bounding boxes have parameters. So bx, by, which is essentially the midpoint in the image, bw, which is the width of the bounding box, and bh, which is the height of the bounding box. And this is trained through our neural network and is also outputted in our target label y. But essentially, object localization is not the most efficient method because, as I mentioned before, object localization is only able to identify and localize one object in view. And if we're inputting this into something like a self-driving car, this essentially will not work, as oftentimes there's multiple objects in view that a self-driving car needs to classify and localize. So this is why we use the sliding window algorithm for object detection. So in this picture, you see that there's 2 cars. That means there's 2 objects in view, and we have to localize them. So for a sliding window algorithm for car detection, essentially our training set looks something like this. So in the input variables, there's pictures of cars and non-cars. And essentially, if we input a picture of a car in our CNN, then our output has to be a 1. And if there's no pictures of a car, and if it's just the background, then the output is a 0. So essentially how the sliding window algorithm works is that there is a small window, and this is inputted into our image. So when this window is inputted into our image, it actually crops a section of the image, and the crop section of the image is inputted into the CNN, and the CNN classifies whether there's a car in this image or if there's not a car in this image. So essentially, as you can see, there's no car in this image, so our CNN outputs a 0. But when there is a car in the image, the CNN outputs a 1. And essentially what happens is the sliding window goes through all of the image in a stride and outputs and localizes where the objects are in the image. But again, this is not efficient because with object detection, it object detection is very computationally costly because it takes a lot of time essentially to gather where the objects are localized in the image, and also it's computationally costly because there's a number of different cropped images you need to input into your CNN. So that's why there's this thing called YOLO algorithm, which is essentially you only look once. And this is an algorithm that has real-time object detection and classification, which is huge because for something like a self-driving car, it is able to see the objects in view and classify them in real time while also localizing the objects in view. And it basically does this because for the YOLO algorithm and its neural network, it only needs one forward propagation in order to make predictions. And and it is a real-time object detection and classification, which provides an immense amount of ability to generalize its objects and classify them. Also, it has an extremely high accuracy, which is rare for algorithms who are able to process images fast. So essentially how the YOLO algorithm works, it mixes together the object localization and the object detection algorithm. And what it does, it takes an image and divides it up into different cells. And each cell is responsible for outputting a number of bounding boxes. And each bounding boxes is responsible for extracting a confidence score. And essentially what this confidence score is, it tells you how high the probability is that the bounding box actually encloses on an object. So in essence, these are the bounding boxes that are outputted through the YOLO algorithm. But what happens is that the higher the confidence score, the higher the probability that the bounding box actually encloses an object, which means that the thicker the bounding box, the higher the confidence score. So as you can tell in this image, the yellow bounding box is the thickest bounding box, which means that it has the highest confidence score that the bounding box is actually enclosing an object, which is the dog. Then what happens is that non-max suppression is put on the YOLO algorithm, and when non-max suppression is put on the YOLO algorithm, it actually extracts all the confidence score, the low confidence scores, which removes the bounding boxes with the low confidence scores, only leaving the actual bounding boxes enclosing an image. So this is essentially how the YOLO algorithm works in a self-driving car, as it is able to identify and classify images in real time, as well as localizing them. So now I've explained to you a little bit about the intuition behind computer vision, but what I'm really excited to show you is actually the applications of computer vision, and the applications of computer vision actually gets me extremely excited, and I hope after you learn about them too, you are also extremely excited. So throughout this whole presentation, I've talked about self-driving cars, and essentially computer vision is essential and integral to self-driving cars because without computer vision, self-driving cars could not identify and localize the objects in view, which then would lead it to not being able to know how to move in its environment. The second one is self-flying autonomous vehicles. This is so exciting to me because this essentially means that our daily transportation can be in the sky. So essentially, companies like Kitty Hawk, what they're doing is that they're building self-flying taxis, and as they're building self-driving taxis, they're building self-flying taxis and use computer vision essentially to identify the objects around it, and it needs to identify the objects around it because they see the vision that self-flying taxis will be a huge part of our future in the next coming years. And this is because there's actually a statistic that 60% of the world's population is going to move into urban areas, which means an exponential increase in traffic and cars on the road, which is why self-flying cars and self-flying autonomous vehicles is a key solution towards this problem. And also Uber is coming up with their own self-flying car vehicle, which is incredible because imagine having a sharing self-flying car vehicle to operate around in. So another one is drones. So drones equipped with computer vision actually have immense potential to be integrated into a number of different fields, such as agriculture, surveillance, detection, etc. And actually what drones with computer vision are able to do, they're able to capture and analyze immense amount of imagery as they're flying above something like a crop field. And drones are actually have huge impact in agriculture as it's able to identify, measure, survey, and actually water the agriculture and help it out with time efficiency extremely. So actually, there's a statistic that in 2050, the world's population will increase to 9 billion people. And when the world's population increases to 9 billion people, this means that there's extreme exponential need for things such as crops and agriculture. And drones can actually help with this in the need for agriculture and farming, as it provides efficiency and less time in planting and harvesting these crops. So there's also surveillance for object detection. Suppose you're at an airport and you want to classify if you want to classify the suitcases in an image. But the thing that I'm extremely excited about is the application of computer vision in healthcare. And I think this is actually an application that will revolutionize the entire healthcare field. And this is because Google actually came out with their own computer vision algorithm to identify breast cancer in mammograms of patients, and they use this to compare to actual trained pathologists. And what happened was that the computer vision algorithm actually had an 89% accuracy, and the pathologist only had a 73% accuracy, which is insane. And the computer vision algorithm was actually faster than the pathologist. So this just means that computer vision can help save so many lives and exponentially increase patient care immensely. And this is huge because a lot of diseases such as cancer, the reason why they're so fatal is because it's extremely hard for humans to diagnose it, especially because of human error, and it's particularly hard to find out. So, which is why computer vision aided with doctors will be able to retrieve an early diagnosis in patients, which will save many lives. So the key takeaways is that computer vision is a key emerging technology that has the potential to be integrated in a number of different fields. And some next steps for me is to actually get into one of these fields like healthcare and actually build something with computer vision to impact this field and make it more efficient better. Thank you.
I'll just ask. Really awesome. What do you think? Okay, let me step back. So there's a lot of talk around blockchain emerging with AI. So these exponential technologies sort of coming together. Where do you see sort of computer vision merging with another exponential technology?
Well, computer vision can aid in a number of different technologies, and I think it has to do mostly with the technologies in healthcare, as I mentioned before, because computer vision has the ability to identify objects that are unable to be seen with the human eye. So I think it has a huge impact in that area.
Can you just tell us where you started? Yeah, no.
Actually, we're already there. There's a number of self-flying autonomous vehicles and self-driving cars are pretty, so we're already there. Essentially, I started artificial intelligence and really focused on computer vision. Was it Yeah, awesome. So essentially, neural network, you want to create as many hidden layers in the neural network to optimize the neural network and increase the accuracy of your neural network. So that's it. And that, and there's detecting neural network, learning neural network. Yeah, it the bank for it to predict if client is likely to stay with the bank. And each client lead it to stay with the bank and leave. Far, I've just worked with basically to train the network on.